So what Mr. Larson's done is to put together all the ways that you can thermodynamically make advantages in an engine. He has adiabatic cylinders and pistons so that they're not robbing heat on compressed conditions, compressed air
Adiabatic
conditions.
means without heat change.
Without heat transfer. So anything that you put in work equivalent that becomes elevated temperature gases, as in air, is heated on compression, stays in the air. He has stratified charge combustion so that he's adding the fuel within such compressed air and burning on a basis that is timed for the fuel purpose, best brake mean effective pressure, or BMEP, so that he gets the use of the fuel value on the power stroke. What else he's showing here is the ability then to transfer the thrust of the piston without side loads to the cylinder to a rod, to a system for making it into torque on a rotary cam. The rotary cam is designed to have 3 lobes per side per revolution, which gives him a net ability to have 24 power strokes per revolution.
24 power strokes per revolution. So there's no crankshaft per se in this engine.
The crankshaft that ordinarily would be used in common engines is absent. Instead, he's managed a system that has no side thrust on the pistons, produces torque on cams instead, and produces a much greater net torque because he has a 3-to-1 torque multiplication by the number of cam lobes that he has per side of revolution. So he has 4 cylinders opposing 4 cylinders, which furthermore then makes a completely balanced engine.
So this is an 8-cylinder engine.
It's a 8-cylinder opposed 4 opposing 4, 24 power strokes per revolution.
So that was the N part of the span equation.
That's the way to have the plan equation work for you with all of these put together in a ensemble of thermodynamic advantages. But further, he's enabled a system, because it has a torque multiplier built in, to use a very low cross-section as for going through the air, through the water, with minimum drag. And further, he's able to package 300 horse in this small unit volume.
What, this engine is 300 horsepower?
It's 300 horsepower, real power, 900 foot-pounds to the output shaft.
So this is the output shaft down here.
It is, and it could be an output shaft on both ends if you wanted to put this as the replacement for the engine, transmission, and differential, and have your drive wheels as many times as you want to have drive wheels, even a earth mover or in a 4x4, for much more control and the ability to turn off either engine on demand.
Either engine? You mean you can turn off either side?
You can turn off either side, and as his cam provides, it'll go backwards as well as forwards on the selection of firing order for the 4 opposing 4. In other words, you can come, stop, immediately start on reverse rotation and provide all-wheel drive with this much clearance because of this much relatively small cross-section and engine extent to do the job of 300 horses that ordinarily would be a very large engine.
So, how many cylinders can it run on, minimal?
Oh, he could loaf on all of these cylinders because he's burning on a stratified charge basis. So he can burn any air-fuel ratio and choose whatever torque he wants to develop.
So not only can you choose the number of cylinders you want to run on, you can determine the charge of all the cylinders.
You can determine the charge of all the cylinders, exactly right.
So you could use the same amount of fuel you would on one cylinder full power, divided across 8 cylinders, and keep all 8 running and moving.
Precisely right, and stay entirely balanced all the way through this regime of operation.
Now we're looking at a prototype model here of the engine. This is not the actual operational engine.
This is a full-size prototype of all the components, so you can see them in, as it turns out, what would be about 220 pounds per 300 horse.
So we can see right in the cylinder down here.
What you'd see is a cutaway so that the piston motion here is expressed as compression over here.
Oh, wait a minute. Let's go over here. You're moving that cylinder one way.
Right.
And this cylinder over here
is coming up on compression.
So
it's going through top dead center and starting power as this one goes through compression.
So you have no wasted movement. It's basically going to be more efficient than a 2-stroke and a 4-cycle engine when one is on
Indeed.
a power stroke, the other one's on a compression stroke.
Well, it's a Larsen cycle. It turns out to have the attributes of a two-stroke without the requirement of having oil in your fuel.
So it's not a straight Otto cycle or diesel cycle. It's named for
Its inventor.
It's named for Mel Larsen.
That's right. And he's furthermore provided for a type of air breathing that is much, much larger in terms of volumetric efficiency than a two-stroke ordinarily could be.
Where's the air intake?
The air intake is here. It comes across on a transfer to the backside of each piston, and then the backside transfers to the combustion chamber through an internal port in this adiabatic assembly.
Mm-hmm.
Because you can't see the valves in there, can you?
No, but know this, they're positively activated valves so that they're not requiring a pressure drop across them for activation.
Oh,
You go from full open to full close without restricting the airflow within.
how about the hydrogen fuel? How does the hydrogen? This engine? What will it run on?
It'll run on anything, but it prefers, for its world record capabilities, to operate on hydrogen for the principles that we've discussed of faster combustion and the ability to run at unthrottled, non-throttled, zero throttling, very far excess air-to-fuel ratios.
So
as
these
needed.
are the PSI injectors that you have detailed in the book Solar Hydrogen Civilization.
They are, as you would see it here, configured for a Hemi head arrangement of fuel distribution within the combustion chamber.
So the head is hemispherical as well.
It is.
And this will inject the hydrogen fuel or natural gas fuel or whatever fuel directly into the cylinder.
It does. It lets the cylinder intake as much air as possible so that it has a much larger inventory of air to support as much more fuel as you choose to burn.
So as we drew earlier on the internal combustion fundamentals area, we showed fuel coming in through a carburetor, mix it with air. We showed fuel being spurted in exactly before the intake valve, and now we're talking about fuel being injected directly into the cylinder itself.
And burning without ever touching any of the components that define the combustion chamber.
Ah, so you're saying, I see the point now. So normal gasoline is going to swirl in by the intake valve, make contact with the cylinder, be ignited, be in contact with everything, and the hydrogen is going in so fast, so quick,
And
at
burning.
the top dead center of the cycle and being ignited at the last minute. And its combustion is so fast it doesn't have time to propagate its heat to the walls and to the valve and to everything it passed on the way.
That's right. In fact, what it is designed to do is to make sure that that hydrogen is completely combusted within surplus air.
Uh-huh.
So that it's adiabatic from the standpoint of the material selection, but it's furthermore adiabatic from the standpoint of surplus air that insulates the combustion.
Now the big difference is we cannot really run surplus air with gasoline in traditional fuels. One, we won't get the detonation that we want, and two, our emissions go all to heck. And but hydrogen has real broad fuel-to-air ability.
It does, but it also, in this instance, is a study in how to make the heat release for the purpose of heating air and not anything that is going to conduct heat and lose heat to the outside world.
Which is one of the reasons this is so efficient.
It is, and then it furthermore gives him an effective expansion that's much larger than the ordinary expansion.
So this engine is going to run more efficient than a standard gasoline engine we use today. It's going to run more efficient than a diesel engine that we're using today.
It'll extend the efficiency envelope in all modes of operation from low torque, low RPM to maximum torque, maximum RPM.
And for large power applications, this thing's going to even run more efficiently than traditional fuel cells we use today.
It does that.
So this is really going to hold the world record for conversion of BTU energy to shaft horsepower.
Testing shows already that Mr. Larsen holds the world's record. Now we need to put this into manufacturing so that it can be enjoyed around the world as a new improvement on thermodynamically, as it turns out, regenerative, heat-conserving adiabatic engine operation.
What is the world record for internal combustion efficiency today?
It depends on the size of the engine, the surface-to-volume ratio, but it ranges from about 45% to about 54%.
45 to 54% for the published world record in efficiency.
That's right.
In my gasoline engine in my car today, 17 to 22%. A good diesel engine, 35 to 44%, depending on who makes it. And so we're talking about this 44 to 54%.
Depending on the size and the application.
And that's without heat recovery.
Well, that's with some heat recovery. This is not taking into account, however, all the ways that we would use virtually all the heat later on.
Right, but this is not 54%, 50%, 48% is not an inflated number because we're
No.
not counting that's shaft horsepower.
That's shaft result from fuel burned.
Okay. We just want to make sure our numbers are nice and clear because a lot of
Sure.
people will say, I got a 70% efficient engine. And when really they're just reclaiming the heat coming off.
Yeah, no. This is the ability to do more than that engine that you might have reported just now, because what you have in the exhaust is the ability to take all the heat without having a water jacket type of separation of low-grade heat from high-grade heat.
So the cooling system on this is there's no water jacket, no radiator system?
There's none.
No radiator.
No radiator.
So as we mentioned earlier, in typical internal combustion fundamentals, rules of thumb, 1/3 of the energy goes to the shaft, 1/3 to the cooling system, 1/3 out the exhaust. This one is not throwing any of that 1/3 into a cooling jacket
That
for
is
the
right.
radiator.
Well, that's the nature of the adiabatic combustion chamber, is to conserve the heat and use it in expansion.
Well, gee, how am I going to keep my car warm in the wintertime in Michigan?
From a heat exchanger to the exhaust. But mind you, this is a breathable exhaust if you choose.
What? Oh, that's right. This is a hydrogen engine,
This
so
is a
the
hydrogen
exhaust
engine.
is going to be water vapor.
Water vapor. Now, if you choose to run it in a mode of operation that has some hydrocarbon in it, then you wouldn't do that. You just do heat exchange. But it is true that if you choose to have humidity all the way down to condensation of the water for potable water purposes, this is the engine to select for the purpose.
And besides, if you had hydrogen on board, you could heat the inside of the vehicle with the hydrogen combustion directly anyways.
Sure, anytime that you choose. But you'd much rather take it on primary production of shaft power, and
Yep.
then secondly, for space heating.
Excellent. Anything else to mention on the engine? Oh,
No.
we mentioned manufacturing. What's the public story on the manufacturing of this world record engine?
Well, it needs to go into mass manufacturing, but it's designed for manufacturability. Every one of the cylinder sets is exactly the same as the other for interchangeability. So you could change from, as may be needed in the field, from this plate out, a piston cylinder combination.
Also, this would have fabulous military and harsh environment applications where you had to do on-the-spot field serviceability. You
Sure.
could run on 7 cylinders.
You could, but you could make a very rapid and interchangeable replacement.
You could grab one off of one vehicle and put it
Sure.
on this one as quickly as you could remove almost 4 bolts.
That's exactly right.
That says a lot.
The rest of it is also designed for manufacturability, and it's particularly designed for manufacturability from the standpoint of the material inventory being much, much less than what we have today
Well,
in all the engine
Let's
selections.
talk about manufacturability. One of the things you're saying when you're saying that people don't realize is there's something in the manufacturing industry called tooling cost.
Indeed.
You have to spend millions of dollars on tools to make each particular item, molds,
That's right.
tools, everything you can think of to produce 10,000 of these a day. And by having less parts and less material, we're talking about half or a third of the tooling involved for this engine than we're talking about a standard engine.
It's probably even less because each of this, as I mentioned, each of these cylinder sets are exactly the same. So you tool for this, you tool for this section, and you're done.
That's a lot. I mean, that says a lot.
It says a lot in terms of beginning costs for production.
Well, this is one very interesting engine, and we can't wait to see this thing in production someday.
On the bench there, yeah, that cam there on the bench,
Yeah?
that would give you a hell of a lot more torque than this little cam does,
That
Is it-
goes up as the
with the same
square of the
cylinders.
radius.
Yes.
So
That's
you
a
could make,
very large cam.
it is. That's,
So
that's
this is
much
a
larger.
300. This is a 300 horsepower engine that we're
Yes.
looking at here, as it denotes down here. But again, in size,
Yes.
this could be a how many cylinder? 1, 5, 10?
Well, this would be a 8-cylinder again, duplicating this progress.
No, but this could be. This is a 300 horsepower. Can you make a 5 horsepower, 10 horsepower,
Sure.
1 horsepower?
Of course, you can make them up or down in size.
1 cylinder, 2 cylinders, 8
Well-
cylinders, 16 cylinders.
Well, it depends on the need. Depends on the application of what turns out to be the optimum for every given application.
But and then
Given-
on the same token, this thing can go smaller. It can also go a lot bigger.
Much larger.
So this could replace a 3,000 horsepower engine. This could replace the large diesel engines in ships that are 3 stories tall. And
Indeed.
so this is not just a 300 horsepower engine. This is a Larson Radex engine on a Larson cycle.
Yes.
You know, like a Wankel engine and a Wankel cycle, and a regular engine on a Otto cycle, and a diesel engine on a diesel cycle. This is a Larson engine on a Larson cycle.
Yeah, and it's small enough in cross-section to go outboard in marine applications. In other words, you could have as many screws overboard with integral engine application as you would choose.
And one engine would back up another engine.
It would be back.
In terms of parts and horsepower and ability, serviceability. If you knew how to fix this engine, you could fix the 3,000 horsepower engine or the 30 horsepower engine.
Virtually, that's right. But virtually the same. It's just a matter of scale.
Outstanding.